Hey, welcome back everyone. And today we're going to be talking about Bode plots. I know this was something that I was very confused with when I first learned it, but hopefully this explanation will make it a lot easier for you. So we're going to follow along with this document that I retrieved online, and I'll also show you guys how to do a simple Bode plot in MATLAB. But firstly, I want to just discuss the basic concept behind it. So initially, you start by determining it's to interpret the input and output effects, both magnitude and phase over the frequency. So what you want to do is first determine your transfer function, and you're going to have your zeros in the numerator and your poles in the denominator. And you want to rewrite these by the numerator and denominator by putting it into standard form. What is standard form? Well, that means that you're going to have a 1 here within these, and you can factor this out. So go ahead and just take a look at that, make sure it makes sense to you. Essentially all they're doing is dividing by z1 up here, so you pull the z1 out, and then you get a 1 here. And same in the denominator. Here they find the magnitude of the transfer function, so you want to replace s with j omega. Those two are synonymous, as you should know. And now here's the part that really you want to pay attention to. So here we have our transfer function in the standard form, and we want to take log 10 of this magnitude and multiply it by 20 because that's putting it into the decibel scale. That's why we do that. So 20 log 10 of h of j omega equals 20 log 10 of this function. And then if you work out the logarithm rules, this is the form that it comes out to right here. And really this is the key to understanding what you'll later do in the, I'll just show you with my mouse. This is the key right here, guys, to understanding what's going on in your Bode plots. And remember that when you hand sketch a Bode plot, it's really just a rough estimation of what the transfer function is doing. You'll see in MATLAB it looks a lot smoother. But the whole reason Bode came up with this is that because it's a quick and dirty way to see the magnitude and phase shift of what your frequency response will be. So we can see the zeros give you positives as well as the constant. When you work out the math here using your logarithm rules, basically addition or multiplication in the numerator becomes addition and division becomes subtraction. So you see this 20 log 10 at these particular points. And so when we sketch, we have a series of rules and an order of operations that we follow for the Bode plot. So you want to include the constant terms, which are the terms out front here, poles and zeros at the origin. So that would be something like this, for instance. Poles and zeros not at the origin, so that would be something like this. And then complex poles and zeros, we'll worry about those later, don't worry about it. If you're into an introductory course, you won't even need to worry about this anyway at this time. So constant terms, such as k, will contribute a straight line at this magnitude. So you just do 20 log 10 of k, and you get a straight line. And when you, I should note at the beginning, when you sketch a Bode plot, you're really just superimposing these effects on one another, as you can see right here. And the black line is going to be that's the net of all these added together. So constant terms, that's when you're starting at the origin. That's why we do it in this order. Poles and zeros not at the origin. So with a 0, you're going to have a rise of 20 dB per decade. So the rule you want to remember is zeros is plus 20 dB per decade. A pole is minus 20 dB per decade. Because a pole, if you look at a transfer function, the pole is what's actually attenuating the frequency, whereas the 0 is boosting it and causing more gain. So the effects of the poles and zeros not at the origin. So the zeros and poles not at the origin are indicated by this, and the expression critical frequency or break frequency is often used. And what this really means is that once you hit that frequency, then you're going to break and raise 20 dBs if it's a 0, or lower 20 dBs if it's a pole. So these are best taught really through examples. And there's a simpler example here, but the one I really want to pay attention to is, let's see, this one. So this one's a little bit more complex, and oftentimes on an exam, you'll see something more similar to this, where it's a little trickier to factor in the beginning. So you want to pay special attention to the factoring rules here and just make sure that you factor correctly. You know, this might give you a second to think about, but really 2s plus 1 is the same as saying s over 0.5. Pretty straightforward there. So remember, when you factor these out, this is all just going to combine, and this is your k, so k equals 100. That's out front. So that's just your straight line at the origin. And we see the red line here, it's all color coded. And then one pull at the origin. So what's our pull at the origin? Let's see. Well, that's this S out front here. So you can see there's nothing attached to this. These terms here are ones that are not at the origin. And then we have 1, 0 at Z1 equals 20. So why is it Z1 equals 20? Well, here we see S over 20 plus 1. So this gives you an indication of what the 0 is. There's a little bit of math behind that, but because this is a fast video, I won't go into it. Just know that this is an indication of what your 0 is. So likewise, these will be your poles, one at 0.5 and one at 40. Okay. So I know I'm going kind of fast here, but I'll slow down just a little bit to explain what's going on in this Bode plot and how you'll be able to do it yourself. So first we draw the line of the K. We're going to draw each one of these individually and then combine them together. This is the foolproof way of doing it. It looks a little cluttered in the beginning when you first do it, but it'll make it so that you can, when you follow along from left to right, you just combine things. You don't really have to think about it. Otherwise, you can get confused and lost and screwed up. So you start with the 40 dB here, and then you're going to do the one pole at the origin, which is the blue line that goes this way, like this, and it starts at, well, I think it's really just a rough estimate here. Let me just make sure. Well, it's 20 dB per decade. They just drew it 20 dB above 0 dB, which is fine. So you can start at 40 dB, and then because you have the pole at the origin, it's going to pull it down. So actually it's starting at 60 dB per decade. 60 dB right here is where we start at the 0 frequency. Okay, so 1, 0 that we have here, the break frequency is at 20. We can see this. Remember, this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So that's the way the log scale works. Get used to reading those because you'll see them a lot. Okay, and then we have yellow, the pole breaks at 0.5, which is right here. And we have another break at 40 for another pole. And then really we just take the net sum of these. So remember, follow the technique. So what we want to do is draw the line of each individual term. Yeah, just making sure it's the same. Draw the line of each individual term on the graph. Follow the combined pole 0 at the origin, which is the line back to the left side of the graph. Add the constant term to where this intersects the left side of the graph, and apply the effects of pole zeros at the origin. So we're starting here, and then we can see here we're pulled down, so this is 40 because it's minus 20, then we have minus 40, which is the effect of this yellow here, so this is decreasing, right? Then here we have a 0 here, which is the green, so becomes less steep, it kind of levels out, and then we're at minus 20 dBs per decade here until we get here, which we have a we have another pole which breaks at 40, so we have minus 40 dB, and that's the last break frequency that we see. So it just continues to attenuate at minus 40 dB per decade. And yeah, so we'll just simply do this in MATLAB too. I've already drawn it up for you. So what you'll have to do is put the transfer function back into this form. You want to put it in the polynomial form in MATLAB. The MATLAB documentation is pretty good if you understand and know what you're doing and know what you're looking for. So yeah, try to focus on the theory, and then the MATLAB should be pretty straightforward. But here it's in the polynomial form, so you'll have to do h equals the transfer function, and then you have the numerator here and the denominator here, and then you simply do a Bode. And you can make it a little bit fancier. I like to do this one just because it looks nicer and it's easier to read. And you can also set the scale of the axis. This one goes from 1 to 100. Ours, we're going to go 1 to 1,000 because that's approximately what 10 to the 3 is. And that's where we see all the action of this one. So I've already done it. If you write out the polynomial, if you multiply and you get this polynomial, this in the this factored polynomial in the polynomial form, you'll get a numerator of this and a denominator of this with this would be like 2s cubed, 80s squared, 1s plus 40, and the denominator just to give you an example and know what you're working with. Again, we want to do a Bode function, and we're doing 1 to 1,000, so that's 10 to the 3. And here we simply see it, and just as I suspected, they did make a mistake. Yeah, so you can see, this was what I wasn't sure of. It does start at a magnitude of 40, and that's the correct way of doing it. They made an error in here, which is why you should always be careful when you download things from the internet. This should be starting actually here. So, good to know that. I'm happy we caught that mistake. I wasn't sure really why this was starting at 60 to begin with. It should be starting at 40, and then you have minus 20 dB per decade, which is caused by the pull at the zero, or the pull at the origin. So, what did we learn today? Well, we gave you the quick and dirty rundown of how to do a Bode plot. And then we also learned double check your work on MATLAB, and it will give you the actual response. And always start at the constant term, which is 40, not 60. And it is in the decibel scale, by the way. So 40 dB is times 100, so gain of 100. So anyway, hope this was helpful to you, and let me know if you need any more help in your engineering coursework. I'd be happy to be of assistance. All right, take care, everyone.